Hello everyone, welcome to my channel. So in this video, I will continue my introduction of some important distribution of a discrete random variable. So in previous video, we already talked about what is a Bernoulli trio, what is binomial distribution, and what is a geometric random variable. So in this video, I want to talk about one more important distribution related to binomial distribution. This is a negative binomial distribution. So similar with our previous process, so here I want to first give you the definition of what is a negative binomial distribution. So a negative binomial distribution is also in a series of Bernoulli trios. So here for this Bernoulli trios, it satisfies the same requirement for our binomial distribution. It's also about here if we have several Bernoulli trios, they should be independent with each other. And then for all of the trios, they have two possible outcomes, a succeed and a failure. And then for each of the trios, the probability of the trio we will get a succeed should keep the constants. So that means here we generally denote it by a small number, a small letter p between 0 and 1. So in this case, so now we define a random variable x, and this is equal the numbers of the trio have R succeed occurs. So then we call this as a negative binomial random variable. So if you compare this with our geometric random variable, what's their difference? For geometric random variable, they define a random variable x equals the number of the trios until the first succeed. However, here for the negative binomial trio, this is until the R succeeds. So you can see if here we assume we have like 5 trios until we have 2 succeed. So then until our first try, we only have 1 succeed. However, the last try, the 5th try, we should have our second succeed. So that means here for this negative binomial random variable, that means how many numbers, this last one should be a trio we get a succeed result, and for previous one they have R minus 1 succeed. So based on this idea, we can get our probability max function. So here the probability max function is look like this. So of course the first term, this one is still a combination. So that means we select R minus 1 objects from total X minus 1 objects. And here we say the order is not matter. So this is unordered arrangement. And then this will times 1 minus p, and here if p is about succeed, right? And then 1 minus p is a probability we will get a failure here. So this means 1 minus p x to power x minus r. So that means if we have a x trio, and then here R of them is succeed. So that means the failures one is x minus r. So that's why the power for our 1 minus p, failure one is x minus r. And then for the succeed part, this is about we have R success. So that means here we have the p to power r. Okay, so this is a little explanation about why we have this p to r and 1 minus p to x minus r. However, for the previous combination before this in the first position of this formula, so why we have here select r minus 1 objects from the total x minus 1 different objects. So this is about the succeed. Like for example, if you assume this x is equal like 5. So as I said, that means here in total we have how many Bernoulli trios? We have a 5th Bernoulli trios. And then for each of them, what possible outcome of them? So we know 5th is a place we get our like second second succeed, so that means like R equal 2. So that means as a fifth trio, this should have our succeed, right? Success here. And then for the previous 4, what we want, we only have one success of this, and the other 3 should be fail. So in this situation, what that means? That means from this 4 trios, we want to select one from them, and we don't care about the order of them. So it means the first one, second one, or third one, actually we don't care about it. So in other words, this means we select one r minus 1 objects from the total x minus 1 objects, and we don't care about the order. So that's why here for this term we will have this part like this value of our combination term. Okay, and then one more thing about this PMF of our negative binomial random variable is about the value of our x. So here, because x is the number of the trios we need to get our success, so here for our success, at least we need to have our trios, right? Like if we are lucky enough, we can get a succeed on each of these try. So here, in other words, for our x, it should be no smaller than our r. So that's why the possible value for our x can be r plus 1, r plus 2 until so larger number. So this is our formula for our PMF. So now let us introduce two important terminology of random variable. So here I want to talk about the mean and variance. So assume if our x is a negative binomial random variable with 2 parameters, the r to describe how many succeed we interested, and then the p of the probability of succeed in each Bernoulli trio. So then the mean, or in other words, the expected value of our random variable x is equal r divided by p. And then the variance of this random variable, or the sigma denoted by sigma square, is equal to r times 1 minus p in numerator divided by p square. So these two formulas actually is computed by the definition of our mean and variance. So mean is a weighted average of all the possible values of our random variable, and the variance is to describe the spread of our possible values. So here, this is if you computing this by the definition of our negative binomial random variable and its PMF, you can get these equations. And if you are interested in this one, please leave comments on under this video, and maybe I can upload a video about this computing in future. Okay, so now let me give a quick example about this part to explain how we can use our idea of the negative binomial distribution to compute some important question. So let's look at this example. So assume we flip a coin repeatedly until we get 3 heads. And then we denoted or define a random variable x as the number of flippings when we stop. So the question is ask us what is the probability x equals 3, and what is mean, and what is the variance. So in this question, if we want to finish the first part, so by the definition of our PMF, probability mass function, the PMF at value 3 actually is the probability of our x equals 3, right? So that means here what we need to know is we just need to know what is the formula for the PMF when we have a negative binomial random variable. And then we just find the correct values for all the parameters we need to compute this. So here by the formula of our PMF of negative binomial random variable, this is equal x minus 1 r1 select r minus 1 objects from r minus 1 objects without care of the order, and times 1 minus p x minus r and pr. So this is our formula. And then what is the value we have here? So here we need the value of p, value of r, and value of x, right, to plug in all of the three parameters into our formula. So p is the probability to get a succeed in each trail. So in the question, what we do in each Bernoulli trail, we flip a coin. And then what we want to define as a succeed. So here the question is about we get 3 head and then stuff. So that means here what we care of a succeed is we get a head. So in other words, this probability, this p is equal to the probability we get a head in each flipping. And then here, because in the question they didn't tell us this is a fair cone or unfair cone. So that means generally we treat this as fair if this is not specified. So in this question, that means here for our p, this is just equal 1/2. Okay, and then what is our r? R is how many succeed in the question they ask. So the question they ask this is 3 succeed, 3 heads, and we stop. So that means in this question our r is equal 3. And the last one is what is our value for x. So here in the question they ask us what is the probability of x equals 3. So that means this is capital X equals small x. So here small x is a position for 3. So here in this question we have small x equals 3. So when we plug in all of these 3 value into our formula, we have our probability capital X equals 3 is equal 3 minus 1, and r is 3 minus 1. And we have 1 minus 1/2 to x minus r, so 3 minus 3, and 1 over 2 to power r, so r is 3, right? So this is what we have. And now what we have is in this question, in the combination here, this is equal actually what? This is equal x minus 1 factorial divided by x minus 1 minus r minus 1 factorial and r minus 1 factorial, right? This is by our definition of a combination. And here, if you compute all of them, you can find this is equal what? This is equal plugging x equals 3 and r equals 3. This is 2 factorial divided by 0 factorial and 2 factorial. So here we know by our property of the factorial, 2 factorial divided by 2 factorial, actually they cancel each other. So we'll have they cancel each other. And what's the value for 0 factorial? Actually this one will equal 1. So that means here for this combination, we have the value of this is equal 1. And then for all other terms, we can compute all of them. But the final answer of this question is 1/8. Okay, so this is what the question, or say like how we can get the answer for the part 1 to compute the probability of capital X equals 3. And then for part 2 about how to compute the mean or mu of this question. So the mean of this question, because we already said this x is a negative binomial random variable. So that means we can use our formula of this mean and variance to compute it. So the only thing we need to do is we just need to plug in all the values here. So here for this mean, because mean is equal r divided by p, so this is r now equals 3, p equal 1/2. So we have the value for our mean is equal 6. And then for sigma square, which is our variance, so this is equal r times 1 minus p divided by p squared. So this is equals 3, 1 minus 1 half divided by 1 half squared, right? So then you can use your calculator to compute this, and the answer will be equal 6. Okay, so now in this example, we have the mean and the variance is equal each other. Both of them are 6. However, this is not a common situation in our example of the negative binomial distribution. Here, because our value p is equal 1 half, it's like the two possible outcomes in each Bernoulli tree are equally likely in ones. So that's why here we have this special situation. However, in a general example of the negative binomial distribution, it won't be as this. So when you compute the mean and the variance of a random variable, you need to plug in the value to both equation and formulas and compute them separately. Okay, so this is my example of the negative binomial distribution. In my next video, I will continue introduce some more important classical distribution of discrete random variable. So please subscribe my channel and see you in my next video.